Yes. So in your last class, we introduced what is a reactive intermediate. First reactive intermediate, that is carbocation. So carbocation is a trivalent carbon electron deficient intermediate which having 3 bonds and having a positive charge. Variable preparations I shown how to prepare it or how to generate a carbocation. Then how to stabilize a carbocation. Then how to detect a carbocation. Then finally chemical properties of a carbocation. So how carbocation involved in chemical reactions. First is rearrangement, later on addition of a nucleophile followed by deprotonation, that is completely depends upon nature of reagent. So based on nature of reagent they may undergo either addition of nucleophile, otherwise deprotonation. Okay. Now second reactive intermediate is carbanion. First is carbocation, that is over. Next, total how many reactive intermediates are there? 6 intermediates. Carbocation, carbanion, free radical, carbene, nitrene, one more is benzene. First we will see about structure and information of carbanion. So carbanion is trivalent carbon intermediate. Trivalent carbon intermediate having what is the charge present on carbanion? Negative charge. It is a trivalent carbon intermediate having negative charge. Okay. Now, how many bonds are present? 3 bonds, 1 negative charge. So indirectly I am saying that it is octet electronic species. Octet electronic species and found to be unstable. So even though they have 8 electrons, it is found to be unstable due to lone pair is not actually belongs to its own, it is belongs to other species. So that's why it is gaining 1 extra electron. Due to that particular reason it is attaining octet, but it is found to be unstable. So it is unstable species and found to be octet electronic species. Next, carbanion, it is a nucleophile. Carbanion is nucleophile, diamagnetic in nature. It is diamagnetic in nature. Carbanion is nucleophile, diamagnetic in nature, and one more, carbanion is also a Lewis base. It is Lewis base. It is Lewis base, and we can also remember it is formally negative charge. We need to represent with a negative charge. Carbanion is formally a negative charged species. Trivalent carbon intermediate having negative charge, octet electrons, and it is found to be nucleophile and Lewis base. It can have a tendency to use their negative charge, and formally this species is negative charged species. Okay. Now this molecule or intermediate is isoelectronic and isovalent with isostructural. Isostructure with which one? Ammonia. So ammonia structure and carbanion structure remain same. Same number of electrons, same structure is known as isoelectronic and isostructural. Isostructure or isostructural, both are same. Isoelectronic means it have same number of electrons as that of ammonia. Isostructural means it having same structure as that of ammonia. That's why they are called isoelectronic and isostructural. So can you write like this? Carbanion having a 2 electrons, and see these are the 3 bonds which are present around this one. Okay, so this is also represented by, you can also write like this, it is also represented by negative charge. You can write a lone pair, otherwise negative charge, both are same. This is its own electron, and what about this? It is comes from a metal, otherwise it may comes from a hydrogen. Here also same. If I write -1 means its own electron combined with a extra electron, that is the meaning. If I write -1, this is its own electron, this electron comes from either hydrogen or else it may be comes from a metal. That's why it is -1. -1 means one lone pair. Now this is also represents similar to ammonia. See, ammonia having how many bond pairs? 3 bond pairs and 1 lone pair of electron. But we should not write negative charge on nitrogen. You can write negative charge on carbon, but we can't write negative charge on nitrogen if they carry trivalency. Why? Because nitrogen having 3 bond pair of electrons and one more, this lone pair, these 2 electrons belongs to nitrogen only. But here these 2 electrons not belongs to carbon. 1 electron belongs to carbon, other electron belongs to either hydrogen or else it may be a metal. That's why carbon bearing negative charge, you can write it as neutral or else negative. But for nitrogen, if I say it is a lone pair, don't write nitrogen with -1 and don't put 3 bonds. You can write only lone pair, but don't write negative charge in this one. Okay. Now, so what is the hybridization involved in carbanion? How many bond pairs are present? 3. 1, 2, 3, and this is 4. 3 bond pairs, 1 lone pair. So now hybridization is sp3. It is similar to tetrahedral carbon. Now what about bond angle? So bond angle is 109 degrees 5 minutes. 109 degrees 28 minutes for tetrahedral carbon, methane. But here angle is less than 109 degrees 28 minutes. And what about here? If you compare the bond angle, it is 107 degrees. And what is the hybridization for methane? Hybridization for methane is sp3. So methane is sp3, it is same way ammonia also sp3, but for methane 109 degrees 28 minutes. This I am saying. Carbon with 4 hydrogens. Now what is the shape here? It is completely tetrahedral. It is tetrahedral sp3 hybridization, and what is an angle? 109 degrees 28 minutes. Now angle is less than this one. Means at this particular place bond pair is replaced by a lone pair. That's why angle is decreases. Bond pair, initially they carry a bond pair. This bond pair is replaced by a lone pair. That's why lone pair, bond pair repulsions are expected. So we know, always remember, lone pair repulsions are repulsions are stronger than lone pair, then bond pair. So here bond pair is there, but here lone pair, bond pair. So now force is very high. That's why your angle is 109 degrees 5 minutes. But what about here? 109 degrees 28 means it is less than which one? Less than tetrahedral angle. Little less than tetrahedral angle. And this is 107 degrees directly. So what is the shape of carbanion? Shape of carbanion is it pyramidal? Geometry is pyramidal geometry. This one is pyramidal. Pyramid geometry. Carbanion having a pyramidal geometry. Methane having a tetrahedral geometry. It is also pyramidal. sp3 with 107, sp3 with 109 degrees 5 minutes. Clear? It is isoelectronic and isostructural with which one? Ammonia. How many electrons are present? 8 electrons. Here also 8 electrons. What is the shape? Pyramidal. It is pyramidal. That's why isostructural. Isostructural means same structure as that of ammonia. Same number of electrons as that of ammonia. Okay? Only differing their bond angle between ammonia and which one? Carbanion. Methyl carbanion. Okay? See, when carbon bearing a lone pair of electron, it is nothing but a negative charge. Okay. Next, here I am writing a R. Next, here I am writing a thick line. This is R dash. Now here I am writing a R double dash. Okay. Is this lone pair of electron is localized or delocalized? It is localized. That's why we are counting as 4. 1, 2, 3, 4. It is not a delocalized lone pair. If lone pair present on carbon, if it is a localized, then only it is hybridization. If any conjugate partner is present, conjugate to this lone pair, they may also undergo delocalization. Right now it is localized. If it is localized, hybridization is sp3. Okay, right now I am saying it is a lone pair, it is localized. Now it is a pyramid structure. Now lone pair orienting right side. Now it can have a tendency to push inside like this. Then what happens? This lone pair comes left side, and see this is R, and what is this? this is R dash, this is R double dash. This is nothing but a pyramidal inversion. What is this? Pyramidal inversion. Now pyramid is towards right side. If I push like this, it will goes to back side. Now what happens? There is an inversion of pyramid takes place. This is called conformation. And this equilibrium is nothing but a dynamic equilibrium. So now pyramidal inversion will give racemic mixture. Remember, now these two isomers are enantiomers. Remember, it is one enantiomer and it is also one more enantiomer of one molecule. So this is 100% one enantiomer, 100% other enantiomer if these three groups are other than conjugate groups. Suppose if I take a pyramid, this is a pyramid. Now three bonds are there, one lone pair is there. If I push this lone pair inside, this will go this side. And what about this bond? This bond goes to right side. Now they will take like this, like an umbrella. Okay, left to right, right to left like that. They are at equilibrium. Now this equilibrium is nothing but a dynamic equilibrium. If any isomers are at dynamic equilibrium, that isomers are called conformers. This will be there in your chapter, separate conformation analysis, one chapter is there. There you will came to know what are conformers, how conformers are going to be produced. Now only one thing you remember, if carbon carry lone pair and three different groups, then this carbon nothing but a chiral center. Okay, now see, this is a lone pair. Now here I am writing a methyl group. Now here I am writing ethyl group. Next here I am writing one isopropyl. Is it a chiral group? Chiral center or not? Yes. When carbon having four different substitutions, otherwise three different substitutions with one lone pair, then that center is also known as chiral center. It is chiral center. Every chiral center, or if molecule having only one chiral center, it will show its second enantiomer. Okay, is it a chiral center? Yes, it is a chiral molecule. One chiral center, in that lone pair should be taken as a one of the different group. So what is a chiral center? Center having four different substitutions, hydrogen, chlorine, bromine, iodine, then that is also a chiral center. Not only hydrogen, you can also take even lone pair. Okay, suppose if I take nitrogen, one lone pair I am taking, this is methyl, now this is ethyl, then see here I am writing hydrogen. Is it a chiral center? Yes, it is a chiral center. Four different substitutions are, in that four different substitutions, at least one, maybe lone pair is also present, that is also a chiral center. So don't think that always definitely they carry either atoms or groups. Even at least one lone pair is present, that is also considered as a new atom or group. In order to identify which one? Chiral center. Now it is a chiral center, here also it is a chiral center. When molecule having only one chiral center, that molecule is said to be, what is it? That molecule is said to be optically active. Now these two are optically active enantiomers. These two enantiomers are interconvertible at equilibrium. If they are interconvertible at equilibrium, these two enantiomers are nothing but a dynamic enantiomers. One separate chapter is there. In this one, right now remember, if any lone pair present on carbon or nitrogen, and if remaining three groups are different, then definitely they will adopt the equilibrium with its second enantiomer. Now you can convert from here to here, here to here. So both are interconvertible enantiomers. Clear? Right. What is PI? Pyramidal inversion. Now it is pyramid or not? Pyramid is going exactly opposite side. That's why it is inversion. What does this symbol indicates? Chiral center. So here you write one point. In carbanions, carbon with 3 different substitutions. Carbon with 3 different substitutions produce, what they produce? Produce chiral center. Produce chiral center. In chiral center, lone pair is also considered. Lone pair is also considered as a new atom or group. Just in your mind, you should keep in your mind that lone pair is also taken as a different atom or group. In carbanions, carbon with 3 different substitutions produce chiral center. Okay, and liberates conformers. And liberates conformers. So just you say this is 1 and this is 2. These 2 are conformers, remember. Liberates conformers 1 and 2. Interconvertible isomers at equilibrium are known as conformers. Can I ask some questions? So what is a carbanion? Electron rich or electron deficient? Electron rich. It is a nucleophile. It is a Lewis base. What is the bond angle of methane? 109 degrees 28 minutes. Is it a Lewis base? Yes, it is Lewis base. What is the structure of carbanion? Pyramidal. So carbanion structure is isoelectronic with which molecule? Ammonia. But there is a difference only in bond angle. So ammonia having 107, but carbanion having 109 degrees 5 minutes. Okay. So and one more thing. If 3 different substitutions are present on carbanion, if it is a localized, is it lone pair localized or delocalized? Localized. So what is the hybridization of carbanion? sp3. What is the structure? Pyramidal structure. You remember that point? If it is a localized, then only sp3. Suppose, remember, I am writing a carbanion like this. Carbon attaches to this one. Is it a negative charge? Can I write negative? Okay. Now how many bond pairs present around this carbon? 3 bond pairs with negative charge. Is it a lone pair? Yes, it is lone pair. Now see, observe clearly. This negative charge is migrating like this. It is not stick on one carbon. Now it is keep moving from first carbon to third carbon. So if it is keep moving, now can I put double bond over here? Can I write negative? Now observe clearly. Now this carbanion negative charge is delocalizing. On that time, don't consider that negative charge while writing hybridization. How many bond pairs are present on this one? 3. How many lone pairs are present? No lone pair right now. Why? Because it is under delocalization. Now what is the hybridization of this carbon? sp2. Be careful. If negative charge is conjugate with double bond or negative charge is conjugate with any conjugated partner, whose hybridization will be decreases. Why? Because negative charge is under delocalization. And see, what is this? It is sp2. And what about this one? sp2 and here also sp2. Now see, is it carbanion is delocalizing or localized? In this one, is it localized or delocalized? Delocalizing. Whenever if it is delocalizing, don't consider that lone pair. Simply ignore it. But whenever if it is localized, you should consider. Is it moving? No, it is not moving. Okay? Like this. Suppose if I take a carbanion, this is pyramidal inversion. Now pyramid lone pair is present here. Now it is moves like this. Now lone pair is towards right side. Now it is moves like this. Lone pair left side. This is called conformer. But right now negative charges keep moving from one carbon to other carbon. This is called conjugation effect. Now is this negative charge under conjugation? No. So then what is the hybridization over here? sp2, and what is this? sp3. And what about this carbon? Now it is sp3. Now it is localized or delocalized? Localized. Localized lone pair always having sp3 hybridization. Clear? Now is it a carbanion or not? Just say the answer. Now I am writing negative charge on this one. Is it carbanion? Yes. What is the hybridization of this one? sp2 or 3? sp2. Why? Because it is under delocalization. So now lone pair is not localized. If it is localized, try to include that lone pair in calculation of hybridization. If it is delocalized, don't include, simply ignore it. Like this. Clear? Now take one question. So you should write like this. The hybridization of carbanion is, what is the hybridization of carbanion? So sp2, sp3, sp, option D, both A and B. What is the hybridization of carbanion? What is the hybridization of carbanion? When they given like this, give priority for sp3. Normal methyl carbanion is known as a carbanions. If they mention strictly carbanion and under conjugation, on that time it may be sp2. But normal if they mention what is a carbanion means methyl carbanion whose hybridization is always sp3. In this one, lone pair is delocalized or localized? Localized. If it is localized, you should consider that lone pair. This is looks very easy, but those who know clear concept, they will confuse. Problem is, if you know the concept, you will confuse. If you don't know the concept, you can give answer sp3. Next, write one more. So carbanion is a diamagnetic neutral dash molecule. Carbanion is a dash molecule. Diamagnetic neutral, paramagnetic neutral, diamagnetic negative molecule. Next, paramagnetic neutral. Paramagnetic neutral. Try to think. Looks very simple, but if they ask perfect question, you will confuse. You require more knowledge on basic terms. Is there any free electron is present in carbanion in the form of non-bonding electron? One electron? No. Definitely pair is there. When paired arrangement is there, and one more point I given, I think so. It is a diamagnetic, formally negative charge. Now what is the answer? Diamagnetic negative molecule. So why it is diamagnetic? All paired arrangement of electrons are present. There is no free electron. There is no free single electron. That's why it is diamagnetic negative molecule. Now this question also asked in exam. Bond angle of carbanion is 120 degrees, 109 degrees 28 minutes, 107 option D, 109 degrees 5 minutes. So generally when sp3 is there and we know it is isoelectronic with ammonia, you will think about 107. But correct answer is 109 degrees 5 minutes. You compare every time one intermediate to other intermediate. Every time you, if any time is there, keep revising second intermediate. Why? Because overall intermediate will be in your mind. Anytime if I ask, you are in a position to say some information about that intermediate. Starting from carbocation, carbanion, free radical. If you know this one, then only we can enter into molecular rearrangements very easily. Why? Because all named reactions, molecular rearrangements related to reactive intermediates only. Next. So structural information is over. Next, go through generations. Generations of carbanion. How to prepare a carbanion, how to generate a carbanion. Now, one of the best method is See, I am taking a hydrocarbon. What is the electronegativity of carbon? Carbon electronegativity is 2.5 and hydrogen electronegativity is 2.1. Okay. Now this bond is not a polar bond, it is a non-polar. It is not a polar bond. What is this bond? Non-polar. Wax. You know wax is a non-polar. It is not soluble in water. Water is a polar. Polar required polar, then only it is soluble. Salt is highly polar. That's why salt is soluble in water. So petrol is a non-polar. Petrol never soluble in water. Here also same. It is a wax. Alkane is a wax. Paraffin nothing but little affinity. Alkanes are nothing but paraffins having little affinity. Wax, best example is wax. Okay, and you will feel even different touch regarding paraffin. Now if I use any base never take proton from this non-polar hydrogen. So reaction is not possible. Why? Because now polarity is not a large in difference. There is little difference in their electronegative difference. 2.5 to 2.1 means only 0.4. So by substituting electron withdrawing group on carbon, then what happens? See, polarity is very rapidly increases. Now this hydrogen is called acidic hydrogen. Normally it is not a acidic hydrogen. By substituting one of the hydrogen with electron withdrawing group, this will withdraw electrons from this carbon, carbon showing deficiency, and this deficiency affects on this hydrogen. Now hydrogen ready to lose proton. If any hydrogen is liberated by corresponding molecule, that will develop, say, electron withdrawing group, and this carbon carry which charge? Negative charge. And what is this? This is nothing but a conjugate base. Now what is this? Acid. Now it is a polar body. Now polar body, it is losing proton under the influence of a base. Now when all are hydrogens around carbon, now this hydrogen never taken by irrespective of the kind of base. If this hydrogen, any one of the hydrogen replaced by electron withdrawing group, definitely bases will take this proton. Now it becomes a acid. But what about here? It is not a acid. Now it is a neutral. It is neutral molecule. Alkanes never deprotonated by normal or very weak strong bases. It is substituted by electron withdrawing group. Now what happens? Polarity increases. Non-polar molecule becomes polar. So see, this is the question. If nitro attaches to CH3, is it CH3 can lose proton? Yes. I am using a base. I am explaining. It may be sodium hydroxide, sodium ethoxide, LDA, etc. Use any base. Now this base will take proton here, and what happens? Can I write like this? CH2 minus. Possible? Now, see, I am using a cyano. Cyano attaches to CH3. Can I lose? One of the proton is get removed out, and can I write CH2 minus or not? Now what is the common thing which you observed here? By substituting hydrogen with electron withdrawing group, polarity increases, it is matches with corresponding base. Okay. Now see, is it possible? I am writing CH3 S double bond O, S double bond O, CH3. Is it possible to remove proton or not? Possible. Where should I remove proton? From CH3. CH3 will don't, after losing proton, what we are generating now? Carbanion. Now this carbanion stabilized by resonance. Is it localized or delocalized? Delocalized. See, if carbon attaches to more number of withdrawing group, what happens? It's pKa. pKa decreases. Nitro taken 3 times. Larger the pKa, greater the basicity. Smaller the pKa, greater the acidity. Here 3 nitro is there, here only 1 nitro is there. Which is more acidic between these two? This is more acidic. Now whose pKa value is very less? Right or not? Okay. You know very well this one, CH3 C double bond OH. Now I am using a base, that is sodium hydroxide in dilute proportions. Now whether this hydrocarbon substituted by electron withdrawing group or not. Suppose if one hydrogen is present, what is that molecule? If hydrogen is present here, what is that molecule? Alkane. Now this hydrogen is replaced by acyl. Now it is a carbonyl compound. Now what is the role of carbonyl compound? Electron withdrawing group. If they withdraw electron, one of the hydrogen removed and forms a carbanion. And what is this? This is called enolate ion. It will help in aldol condensation. Many reactions are there regarding carbanion. Carbocation having very few reactions, but approximately 90% of your organic reactions are belongs to carbanion. Aldol condensation, Noe-Venegel, Perkin, Stobie, almost all maximum condensation reactions belongs to carbanion. See, base will take proton here. Now you will get a carbanion. Carbanion is generated which is involved in condensation. Okay. Now not only this, I am taking one more. This is called ester, right? Is it electron withdrawing group attaches to CH3? Yes. Now what I am doing is I am using NaOET base. Now this ETO minus will take proton here and it is eliminates in the form of ETOH. Can I write CH2 minus C double bond OET. Is it a carbanion? Yes, it is a carbanion. Okay, and you know one more thing, after losing proton by a phenol, see this is phenol, right? Phenol on treatment with a base, then this will lose proton and forms a phenoxadiene. Now that phenoxadiene is involving in resonance with, what do you expect? If it is involved in resonance, what is the answer? You will get carbanion. What is this? Carbanion. Between oxygen and carbanion, which is more nucleophilic? Between oxygen and this carbanion, see here oxygen carry O minus, now carbon carry O minus. Between this oxygen and carbanion, which is more nucleophilic, which is a powerful? Carbanion. That's why Riemann-Tiemann reaction takes place at ortho position only. We are not adding electrophile on oxygen. Why? Because between O minus and C minus, which is highly unstable, C minus, that's why it can catch electrophile very fastly. But when oxygen carry negative charge, it is very relaxed. Why? Because it is a high electronegative element, but carbon is not a high electronegative. Bearing negative charge is found to be unstable. Due to its instability, it can take electrophile. Clear? So every time what we are generating? Carbanion. So 90% of named reactions, 90% of rearrangements, condensation reactions, elimination reactions are belongs to carbanions only. Be careful with carbanion. Okay, generation of carbanion is very, very important one. Once if you know how to generate, then it is very easy to understand how to write a reaction. Take this. This is sulfur. Here you should write, it is a methane. Methane is a non-polar molecule, never involved in deprotonation with a base. So if you want to increase whose acidity, we require a electron withdrawing group. Every time we need to compare with a alkane only. Why we are comparing with alkane? Alkanes are 100% saturated molecules. What is our ultimate target? Saturation or not? Satisfaction. If we don't satisfy, once if you satisfy, we won't react. Right or not? Whether you are stable or unstable. You are unstable, that's why you came here. If you stable, you won't stay here, you will go to Himalayas only. So every organic molecule want to settle down as a alkane. They will compare with alkane only. I want to behave like a alkane. Why? Because alkanes are, they saturated hydrocarbons. But what about highly unsatisfied molecules are alkenes only. Alkenes are highly unsatisfied. That's why many chemical reactions are there. See, total organic chemistry depends on alkane and triple bond only. When double bond comes, that will give instability within the molecule. But when single bonds are present, satisfy. So no reaction. They never respond with any kind of acid and base. Why? Because they are already satisfied. That's why organic molecule always they will compare with their stability with alkane. This is my stability, and what about alkane stability? One carbon is there, what is your stability? One carbon is there, what about my stability? I want to compare my stability with this one. Every time this comparison will be observed. So that's why each and every molecule whose stability always comparable with a alkane. That's why alkanes are also known as paraffins, having very little affinity, and these molecules are 100% saturated hydrocarbon skeletons. They never participates in more number of chemical reaction. If a satisfied person is came, if you want to influence them, we need to maintain a drastic conditions. Right or not? Normal condition, they won't respond. Why? Because they are satisfied. We need to use a powerful conditions. That's why thermal conditions photochemical conditions are required to participate? Alkane. Alkanes having very less chemical reactions because of saturation. Always try to write arrow from nucleophile to electrophile. Be careful while writing arrow, try to write tail from nucleophile or base, head towards electrophile. Suppose if electrophile is present here and if nucleophile is present here, don't write like this, it is wrong. Always tail from nucleophile, head from electrophile side. Whatever direction you want to write, don't think it is right. Always some rules will be there. Always base will take this proton. Base will take this proton from this hydrogen. So suppose here 3 hydrogens are there, 1 hydrogen. This hydrogen is taken by this base or nucleophile. Nucleophile to electrophile. Base to acid. That is a rule. So where it will helps? It will helps in Riemann-Tiemann reaction. Phenol after losing proton forms a phenoxidine. It is get resonance stabilized by carbanion as well as oxidine. This is called phenoxidine. These two. Resonance stabilized phenoxidines. So first is stable, now it is unstable. Now unstable will participate in reaction. Okay, see, this is carbon-carbon triple bond. Is it carbon-carbon triple bond is acidic in nature? Yes. Now what is the charge present on sodium? Positive and this is negative. This will take this proton and this will migrate out. Now carbon carry which charge? Carbon carry negative charge. Now is it stable or unstable? Is it stable or unstable? This is stable. Why? Because this negative charge very closer to sp carbon. Okay. Why? Because sp electronegativity is very high as compared to sp2. Same reagent, remember, if I want to participate reaction with a soda amide, now this reagent never reacts with this. Soda amide never reacts with a double bonded hydrogen. Okay, this reaction is not possible. Whose basicity not matches with this hydrogen. Only LDA can react. Lithium OMC can react. Why? Because lithium OMC LDAs are powerful bases. Alkyl lithium in presence of THF, N-butyl lithium. So this is a base proton. It can take this proton. And finally, see, you may get carbon hydrogen double bond and here hydrogen, and what is the charge? Negative. This negative charge is stabilized by lithium. So this positive negative are represented like this. This is lithium. This is called lithium OMC. Okay? Triple bonded hydrogen easily taken by soda amide, but double bonded hydrogen is unable to captured by soda amide, which indicates that it is a weak acid and weak base. So for a weak acid, if you want to use a weak base, okay, normally it is also a strong, but in order to take this proton, it is a weak base. In order to take this proton, we require a powerful bases. Only LDA, lithium disopropylamide, and one more is alkyl lithium can take this proton, and finally forms a lithium OMC. What is the charge here? Negative, and this is positive. Okay, and one more. Suppose if I take a cyclopentadiene, here how many hydrogens are present? 2 hydrogens are present. Now if I use a base, is it possible to liberate a proton? Yes, it will take proton, it will migrate out. So why it is taking proton? Why? Because molecule attains negative charge, right? Is it aromatic or anti-aromatic? Now it is aromatic. Now this base have a tendency to take this proton. After deprotonation, if molecule attains aromaticity, now this molecule ready to lose proton and forms a carbanion. And one more, I am using cyclooctatetraene. This is cyclooctatetraene. Now I am using a metal. So what is that metal? I am using zinc metal, otherwise copper. Suppose if copper 2 equivalents I am taking, so now 2 equivalents of copper can donate 1 electron and finally forms 2 equivalents of copper plus 1. It is donating how many electrons to this nucleus? 2 electrons. Every copper 1 electron, 2 copper 2 electron. Now finally, how many membered ring it is? 8 membered ring. Now how many electrons are delocalizing? Here 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 2. Total? How many electrons are delocalizing? 10 pi electrons are delocalizing and this molecule is found to be aromatic. Is it a carbanion? Yes, it is a carbanion. So every time what I am generating? Carbanion. See, if molecule have a tendency to attain aromaticity after losing proton, it is a powerful acid. Why? Because that anion involved in delocalization and they are attaining aromaticity. Suppose anion attains anti-aromaticity, it is not a strong acid. It is a strong acid or not? Yes, it can lose proton and forms a aromatic molecule. Now this molecule nucleus can take electrons and forms a anion. Now here 10 pi electron delocalization, now this molecule is aromatic in nature. Right. So what is the name of this molecule? Cyclooctatetraene. Cyclooctatetraene, what is the shape here? Tub shape. So what kind of aromaticity you will expect for this one? Aromatic or anti-aromatic or non-aromatic? Non-aromatic. Non-planar, non-aromatic. Clear? Now this is stability, already in GOC explained, just few examples I will give and I will go through detection and chemical reactions. Stability. Is it electron rich or not? Yes. So suppose if I substitute donating groups, here one donor, here 2 donors are present and carbanion carry 3 donors. So which is more stable? It is already electron rich, now it is giving more electrons. Very high electron density present in this one. As number of donors increases, stability decreases. So first one is more stable than second one, third one and fourth one. Suppose if any electron withdrawing group is present, nitro attaches to CH2. Now how many nitros? 2 nitros I am saying, CH minus. and if I take 3 nitros, C minus, which is more stable? Third one is more stable than second one and first one. As withdrawing groups increases, stability increases. Suppose if I take a carbanion and here nitro is there, and here I am writing a cyano, and here I am writing a hydroxy, which is more stable? First one is more stable than second one is more stable than third one. So which indicates that withdrawing groups strength increases, stability also increases. So many examples already given. In case of GOC, carbanion stability, just revise in that one. This is CH2 minus, CH2 minus, benzene carry 3. So which is more stable? Which is more stable? Third one is more stable than second one is more stable than first one, right? Why? Because more number of resonating structures. As number of resonating structures increases, stability increase or not? Here carbanion and I am writing carbanion. Which is more stable? More number of resonating structures, greater will be the stability. So first one is more stable than second one and then third one. This all points already explained in GOC, just go through it. Okay? So electron donating group decreases stability, withdrawing groups increases stability. As electron withdrawing group strength increases, stability also increases. And here as conjugations increases, stability also increases. As delocalization time increases, stability also increases. Clear? So this is detection or trapping of a carbanion. How to identify carbanion? Detection method. So very easy. So only negative mass spectrometry, used to identify carbanion. Carbanions are identified by negative mass spectrometry. It is not included in your syllabus. It is one of the easiest method, but that instrumentation is expensive in cost. That's why in your IITs, even central universities also, this is not available. Okay, but this is exists. Negative mass spectrometry is there, but it is too much expensive. Okay, it is approximately similar to carbocation. CH3 minus, it is also expressed in terms of m by z. Mass by valency. How much? 15 by 1. 15. And if I write CH3, CH2 minus, how much m by z value? Now it is 29. 15, 29. And can I write 43 for a isopropyl carbanion? What is m by z value? That is 43. As it is positive mass spectrometry only, but in case of positive mass spectrometry, we will use positive charge, but here negative charge. Even HNMR also helps, but value is very, very closer to 0. That's why HNMR is not a best spectroscopy to identify negative ions. It is best only for positive ions. Why? Because more deficiency, greater the ability of identifying non-equivalent protons. Okay? For identifying negative ion, best method is negative mass spectrometry. Now, this is last one in case of carbanion chemical reactions. So, what kind of chemical reactions you will expect for carbocation? Carbocation will undergo rearrangement first, then followed by addition of nucleophile, elimination of proton. But carbanion having many reactions. Okay, first one is CC condensation reaction. CC condensation reaction. This you will learn in case of individual chapters. Alkane, alkene, alkane, there you will learn, but I will give some examples which are involved in CC condensation. Okay, best example for in this case is, what is this? Aldol condensation. You know aldol condensation? Okay, next is benzoin condensation. Benzoin condensation. Then Claisen condensation. Claisen condensation. Okay, Claisen condensation. Next, Perkin reaction, also called Perkin condensation. Noe-Venegal reaction. Next, we can also go through Noe-Venegal, K-N-O-E-V-E-N-A-G-L, Noe-Venegal. Okay, next we can also go through Manish reaction. Manish reaction. So individually you will learn later. Right now I am giving only reactions, but these all reactions having carbanion as an intermediate, and that carbanion responsible for condensation. We will initiate carbanion, that carbanion involved in condensation. That is the simple technique in this one. Okay, so you can also go through Michael addition. Michael addition reaction. Michael addition. Okay. Next, RTR. What is RTR reaction? Riemann-Tiemann reaction. Claisen-Smith reaction. Many reactions are there. Claisen-Smith reaction. Dickmann reaction, Thorpe-Ziegler reaction. Almost all maximum number of name reactions belongs to this one only. This all are aldol type of reactions. Okay, acetylene condensation, benzoin condensation, benzylic acid rearrangement. Everywhere you can expect a condensation reactions here. Okay, so you can also take benzylic acid rearrangement. Benzylic acid rearrangement. So this rearrangement also includes CC condensation. This rearrangement also includes CC condensation. So why we are learning here? We are not going to learn this each and every reaction right now. Separate area is there for this one. There I will explain. But right now one example I will give, which will involve CC condensation. What is CC condensation? Carbon-carbon forms a new bond which is initiated by a carbanion. So best example is, try to identify this. I am taking a CS3 C double bond OH. Now I am using a dilute sodium hydroxide. Mild base I am using. What happens? If I use mild base, what happens? This base will take proton from here and this will forms CS2 C double bond OH. What is this? GOC is over. Many examples I given. This will migrate here and this will transfer it. Now this is get stabilized by conjugation, also called enolate ion. You remember this one, enolate ion. It may be a methyl or it may be alkoxy or it may be chlorine, bromine, what it may be. If carbanion and oxygen involve in conjugation, if they involve in delocalization, that ion is known as what? Enolate. Enolate ion. Clear? That is called enolate ion. Now this is your first molecule of carbonyl compound which will develop a carbanion. Now what happens? Say I am using a second molecule. This is second molecule. This is first molecule. Now this is second molecule. First molecule converts into the form of enolate ion. So that enolate ion will attack on this enolate ion. You can take either this one or this one. You can write here. This is your first molecule. This is first. First converted to enolate. Now first attacking on second molecule. When first attacking on second molecule, here it will attack and this will migrate out. Now which two are attracting together? Electrophile, what is the charge here? Partial positive, and what is the charge here? Can I write these two? Anyone or not? So what is the charge here? Negative. Negative positive, what happens? Condensation. So when they condense together, this is CH3, CO minus, and here hydrogen. Can I write one more CH2? CH2, C double bond OH. Can I write? If this bond comes here, this double bond carry negative charge on carbon. Now this negative charge attacks on this positive. Now see here what is observing now. What is this? Bond formation. That is called condensation. Now this condensation is due to carbanion. Like this, every condensation, same process. That's why aldol, Noivenigal, Perkin, Stobie, everywhere it is a common concept. Generate a carbanion, attack on other carbon which having a positive charge. This is a common thing. So it may be a Perkin, Noivenigal, Claisen, everywhere same concept. First use a base, generate a carbanion, attack on other molecule which carry positive charge. So both carbons carry positive and negative, condense together and forms a condensation reaction. Finally it will take proton from aqueous medium, and what is your final answer? This is CHOH, and what is this? CH2 C double bond OH. What is this? Alpha beta. Beta hydroxyaldehydes are known as aldol. What is this reaction? Aldol condensation. So if I use the word condensation in organic chemistry, CC condensation if I use the word CC condensation, this carbon comes from enolate ion, this carbon comes from carbonyl carbon. Enolate ion shows carbanion, carbonyl carbon carry positive charge, they will condense together. So final target is what we need to generate? Carbanion. If you generate carbanion, already we know carbonyl compound is already available. So generate carbanion, attack on carbonyl, you will get a condensation reactions. That's why many reactions are available in carbanion synthesis. Clear? If you know aldol condensation, approximately 10 name reactions will be in your hands. Aldol condensation, acetylene, benzoin, Noivenigal, Perkin reaction, Claisen-Smith reaction, Claisen condensation, Thorpe-Ziegler reaction, Michael addition, Mannish reaction, what not. Approximately 10 standard name reactions will be in your hand. If you know the common concept of deprotonation followed by generation of a carbanion, the generated carbanion will attack on second molecule, forms a CC condensation product. Take this. Clear? So this you will learn individually in your rearrangements, some you will learn in individual chapters. No need to worry, but only one common point. We are creating a new bond between two carbons which is initiated by a carbanion, that's it. So, do you know OMCs? See, here I am taking a methyl bromide. Now I am using a magnesium. Magnesium in dry ether. What happens? Magnesium is inserted between carbon and halogen. So what is the charge present initially on this carbon? partial positive. What about halogen? Negative, right? But when magnesium is introduced between carbon and halogen, okay, remember, carbon carry negative charge, magnesium carry positive charge. Remember now, what we are converted? Carbocation we are converting into carbanion. Once if carbanion is generated, then what is your next reaction? Condensation reaction. Carbanion attacks on carbon dioxide, this will migrate out. Now this carry which charge? Negative. This negative takes MgBr. So can I write like this, C double bond O, this methyl will attack here. Now this will carry negative, this negative takes magnesium and what is this? Br. Now this is on hydrolysis. What happens? What is the charge present on oxygen? Negative, and here it is positive. This negative takes proton and finally see C double bond O CH3 and this is hydrogen. What is this? Carboxylic acid. Finally see every time what is going on here between these two? Condensation generally. Actually there is a new CC bond between carbon and carbon. Initially it is a carbocation. See, is it a carbocation? Carbon dioxide is electrophile. So what kind of charge you will expect on this carbon? Positive. And what about charge here? Is it positive positive? Can you convert a new bond? Is it positive positive acceptable? No. Positive positive never acceptable. That's why we are converting into OMC. In every OMC, if I use the word OMC, carbon carry which charge? Negative. This organic part always acts as a base as well as nucleophile. Now this anion attacks on this carbon, developing a new CC bond. Further protonation leads to form carboxylic acid. So why we are converting into OMC? Simple logic. Why we are converting into OMC? Why? Because this electrophile we want to make a bond with this other electrophile, but they are not acceptable. So we are diverting them. We are converting this electrophilic center into nucleophilic center, then we are attaching them and we are preparing a new organic molecule. This is organic synthesis. Total reagents, this concept only. Lithium OMC, magnesium OMC, copper OMC, everything is this one. They will take one organohalide, they will prepare one OMC, then they will create opposite charge. Okay, then this will attacks on this electrophilic center. Further hydrolysis, you will get a new organic molecule. Right. You write charges clearly. If you know charges clearly, then you will understand concept. A writing reaction is not a great thing. Everyone can write, even if books also it is available. But try to understand the technique. What we are doing, what is the use of carbanion? Initially carbocation, that won't fuse with this carbon. That's why we are generating carbanion by converting them into carbanion. Initially it is a carbocation, now we are converting them into carbanion, then we are participating. So one more C. This is phenol. Clear? Phenol on deprotonation by a base. I am using sodium hydroxide, but actually sodium hydroxide not reacts with phenol, but by maintaining drastic conditions or suitable thermal conditions possible to react. Okay? So when I reacts with sodium hydroxide, what is the answer? You will get a phenoxide ion which is stabilized by sodium. So now this anion conjugate with this carbon. Now this carbon is ready to participate. It won't allow to participate oxygen in reaction. Why? Because it will say I am more reactive, so you try to allow me so that I can affect that electrophile very fastly than oxygen. So now what I am taking is I am taking a carbon dioxide. Now this negative charge migrate here, this will attach here and this will migrate out. Then what will expect? What will expect? Double bond and this will carry C double bond and what is this? O. Minus or not? This minus is stabilized by this negative charge, partial negative and sodium. Okay. Now this is a chelation establishes at ortho, that's why ortho is major. Now this hydrogen involved in tautomerism. After tautomerism, what you will expect? You will get aromatic ring or not? Now this will carry hydrogen, now this will carry C double bond O, now this is Na plus. Now this Na plus is get stabilized by this oxygen. Now there is a slight interaction is present over here, it is not a strong interaction, it is a very slight interaction. Now after getting this, can I add water molecule? If I add water molecule, what is your final answer? This is OH and what is this? C double bond OH. What we prepared? Phenol to salicylic acid. It is one name reaction actually. What is this reaction? This is called Kolb-Smith reaction. This is Kolb-Smith reaction. Kolb-Smith reaction, conversion of phenol to salicylic acid. Phenol is converted to salicylic acid on reacting with sodium hydroxide in carbon dioxide. So what is observed here? This carbon, what is the charge we are created? This carbon, negative charge. Negative charge means partial negative. This partial negative attacks on which carbon? Partial positive. Is it matching or not? Negative attaches to positive and they undergo condensation. That is a target. Kolb-Smith reaction, remember, Kolb-Smith reaction used to convert phenol to salicylic acid. Ortho is predominated as compared to para. Ortho is predominated as compared to para. Why? Because ortho stabilized by chelation. This reaction not possible with potassium hydroxide. Kolb-Smith is not possible with potassium hydroxide. Potassium hydroxide should not be used in Kolb-Smith. Why? Because cation is large sized, whose size is not fixed over here. So don't use potassium hydroxide in Kolb-Smith, use only sodium hydroxide. It will cover one more time in phenol chapter. Alcohols chapter is there in your syllabus. There I will explain total chemical reactions, complete mechanism will explain, but same mechanism is same only. But why sodium hydroxide is preferred, why not potassium hydroxide? Key reason is potassium having a large size, whose size cannot fit in this cavity. MIDT, Kolb-Smith reaction, SCH MIDT, conversion of phenol to salicylic acid in presence of sodium hydroxide in carbon dioxide. Clear? So that is condensation. Second one is elimination reaction. They involve in elimination. Elimination, substitution, chain lengthening, rearrangement, condensation. 5 reactions are possible for carbanion. Clear? Now, see, here I am taking a pyridine. This is known one for you. This is pyridine. Pyridine carry one lone pair of electron which can have a tendency to take proton from carboxylic acid, especially ortho substituted. This will take this proton and migrate here. So after migration, what you will expect? Nitrogen carry positive charge, and what about this? This will carry C double bond O. Now this will undergo elimination here. Once if they undergo elimination, carbon carry which charge? Carbanion. What we generated? Carbanion. And what about this? Hydrogen. Now this negative ion is very closer, this will take proton, and finally there is a formation of what? Pyridine. So what is this? Elimination. Now elimination proceeds through carbanion. What is intermediate now? Carbanion. This carbanion is stabilized by carbocation addition, so that's why this is completely derived by which one? Carbanion intermediate. So can I use this example in case of, now see the specialty of heterocyclic compounds. If I use indole, and here I am using C double bond OH, is it possible to undergo decarboxylation? Can I remove carbon dioxide from indole or not? Is it indole first of all? Yes, it is indole. Now carbon dioxide can be removed from here or not? So now one point to explain. This is a center where electrophiles get attacked here. Now migrate here and transfer here. Here you will get which charge? Negative. That negative takes proton. Do you know mechanism already given? See in heterocycles. Then this is involved in elimination. Can I use this one? Pyridine with this one. Carboxylic acid at which position? Second position. Is it involved in decarboxylation? Decarboxylation proceeds through which one? Carbanion. Decarboxylation here you will get which charge? Carbanion. Now is it possible to undergo decarboxylation with this? Carboxylic acid at third position. Possible? No. Carboxylic acid at fourth position. Possible? No. So here there is no intermediate carbanion formation takes place, but here formation takes place, that's why they undergo elimination. What we are eliminating now? Carbon dioxide eliminating via carbanion intermediate. So what is our target? Our target is to generate a carbanion. In order to generate a carbanion, I am taking help from a base. This base may donate electron and create a carbanion, otherwise it may take proton and eliminate one group and create a carbanion. So what is eliminating group now? Carbon dioxide. Carbon dioxide is eliminated, created one carbanion. Here also same. Remove this carbon dioxide, create a carbanion, and this carbanion one more time migrate, and here you will get initially positive, that becomes a neutral charge. Okay, that is elimination. So here you write wrong symbol, which indicates that no elimination. Why? Because not easy to generate carbanion by using this base. Now base is helping to generate carbanion. Here this is also helping to generate carbanion, but there is no help from this one, no carbanion. This question is commonly asking in CSR exam. Identify the order of decarboxylation. One question also given in heterocycles. This one and normal benzoic acid are given. This is first, and next this one, next benzoic acid. Order of decarboxylation. Over. No. That is elimination. Next, third reaction is substitution. Just listen carefully, I will give time. See, this carbon carries C double bond O and it carry pH. Now here I am writing a dotted line, this is ethyl. Now here I am writing a methyl, which is a thick line. Now here I am writing one hydrogen, right? Is it a active carbon? Yes, it is active carbon carry active hydrogen, nothing but a acidic hydrogen. Now this is on treatment with a OD, it is nothing but a deuterated base which is diluted by deuterated water. It is a base diluted by deuterated water. Okay. Now what happens, see, this OD minus will take proton and this will carry which charge? Negative. Now on this carbon what I am removing now? Hydrogen. Hydrogen in the form of H plus or not? So it is electrophile. Is it electrophile or not? So after getting this, what you will get here now? Negative charge. So that negative charge, so this I am writing directly, this is ET. Next, what about next? This is Me. Thick line or not? Now see, this negative charge after getting, that is enolate ion. After enolate ion you will get double bond and here you will get which charge? Negative. If it is coming back one more time, it will attack two directions. One is from above, other is from below. Above direction as it is, here you will get deuterium, and what about below direction? Below direction you will get this. This is pH. Now this is carbon. You can write like this. This is pH, this is C double bond, and this is carbon. I am writing thick line. Can I write one more ethyl? This is ethyl and I am writing one more hydrogen. You can also write in one more way. This you write down above direction, you can also write in below direction by keeping these two in one plane. Now what is the relation now? This relation is racemic mixture. It is a racemic mixture. Racemic mixture nothing but two enantiomers. After deprotonation you will get a carbanion. This carbanion involved in resonance and forms a enolate ion. Now here you will get which charge? Negative charge. Like this you will get. Actually you will get this one. Okay, whenever if it is come back and they may attack here, two possibilities, above deuterium, below deuterium. That two I am writing in other way. Now what is the relation between these two? 50% of enantiomer, 50% of other enantiomer. Now what is D? D in the form of? D is coming in the form of electrophile or nucleophile? Electrophile. Here hydrogen is removed in terms of electrophile. So when base is added on this carbon, one electrophile is removed and other electrophile is added. Then what is this reaction? Which reaction? Electrophilic substitution. So this is called an example of SC1, unimolecular electrophilic substitution. Not SN1. SN1 is different. That is nucleophilic substitution. Right now it is electrophilic substitution. If you want to substitute electrophile, what we need to create? Nucleophile. What is the nucleophile here? Carbanion. Finally, carbanion involved in substitution reaction. Clear? It is very easy. See, suppose if I take a carbonyl compound, this is carbonyl and here one more carbonyl. Now here how many hydrogens are present? Two hydrogens. Now I am using NaOET. NaOET is a base or not? This base takes proton here and forms carbanion or not? So you will get carbanion. Now this carbanion will attacks on one electrophile, methyl bromide. Can attack this one and this will migrate out. So and finally what happens? There is a alkylation reaction takes place or not? What is this? CH3 and here hydrogen. What is this reaction? On this carbon one electrophile is present. That electrophile I removed and I am attacking one more electrophile. Now this base taking this proton. What is the charge present on proton? Positive charge. What about this base? What is the charge? Negative. Negative takes this proton. Now hydrogen in the form of proton initially. Now this is what? Positive only. Proton substituted by other electrophile. That's why it is called electrophilic substitution. Clear? Right. So this concept one more time comes in stereochemistry. There I will explain perfectly. So right now remember, you will get a enolate ion. Now this deuterium will come from two directions, above as well as below. So here deuterium, here also write deuterium, not hydrogen, deuterium. It is also called deuterium exchange reaction. So which intermediate is helping for substitution? Carbanion, that is a concept. Which intermediate is helping for elimination? Carbanion. Which intermediate is helping for condensation? Carbanion. So like that, intermediates will play an important role. You try to focus on key point. What we are learning? What is our area to learn? We are learning reactive intermediate carbanion. Where every time you think about, sir is explaining this concept, where carbanion is included. Like that you need to think. If I explain free radical, think about free radicals. Every step you think about free radical. How free radical helping in a chemical reaction? How carbanion is helping in a chemical reaction? Carbocation, carbene, nitrogen, etc. Benzene. If you know these 6, pericyclic is dead easy for you. Okay, why? Because in pericyclic reaction, insertion of carbene starting with a carbene, okay, and if you participate reaction with a cation, radical, anion, etc. So you should know about where charge is localized and delocalized. Clear? Now this is chain lengthening reaction. Chain lengthening reaction. Chain lengthening reaction. So see, if you observe clearly, carbon-carbon triple bonded hydrogen, it is acidic in nature or not? How to remove this hydrogen? By using soda amide. What is the charge expected on nitrogen? Negative. This will take proton, this will migrate it. So after migration, what is intermediate generated here? Carbanion. So this carbanion will attack on one more methyl bromide. Now this will attack here and this will migrate here. And finally see, 2 carbon become, how many carbons you are getting? 3 carbons. Length is increased or not? So now chain lengthening takes place with which intermediate? Carbanion. Suppose if I use one more, soda amide, one more time I am reacting with a methyl bromide. What is the answer? So can I write one more? This amide will take this proton and finally forms carbon-carbon triple bond. Chain lengthening reaction. Okay. Next. This is last reaction for carbanion. That is rearrangements. Rearrangements also possible with carbanion. Carbocation, can you give one rearrangement? Pinacol, pinaclone rearrangement. In the same way, carbanion rearrangement reactions are possible. So best example is C. I am taking a CH3, nitrogen, CH3 and here one more CH3 and this is CH2 and this is pH. Okay. Now I am using phenyl lithium. What is phenyl in this one? Negative ion or positive ion? Negative. Negative ion means it is a basic in nature. Always universal organic solvent is THF. It is a common organic solvent for most of the OMCs. Now nitrogen carry which charge? Positive. quaternary ammonium. What is this? Quaternary ammonium. Now nitrogen is a withdrawing group for adjacent carbons. Whichever carbon nitrogen is very weak towards this base, that may undergo deprotonation. Now this carbon having phenyl as well as nitrogen, so this is more acidic. Now this base takes proton from this carbon. So after taking proton, now can I write like this? This is CH3 and here CH3, and what about here? What will get? Minus. And what is this? pH. Can I write like this? And that negative ion is stabilized by which one? Lithium. Now see, what is intermediate here now? Carbon ion. Now intermediate develops, and that intermediate helping for lengthening of chain. Intermediate in last case develops, and that is helping for substitution, elimination, condensation. Now anion is helping for rearrangement. One group migrate from one place to other place. What is rearrangement? What is rearrangement? One atom or group may move from one part of the molecule to other part of the molecule. It won't move other molecule. It won't jump from one molecule to other molecule. That is called intermolecular. Intramolecular means they may change their places. How you are changing your places in classroom? So here also it will change their place, but still you are in a class only. Here also same. Now this methyl initially present on where? Nitrogen. Now it is migrating from nitrogen to carbon. Now see, this negative charge attacks on this carbon. Now these electrons are migrates on nitrogen. So if they migrates, what will you expect? Nitrogen carry which charge? Neutral or not? It is neutral. Then what about this CH? CH3 is migrated, and see this is pH. Now how this CH3 is migrating? It is migrating from first carbon to second carbon or not? Or first atom to second atom? This is first atom and this is second atom. Now from first atom, methyl migrating from nitrogen to carbon. Initially where this methyl is present? On nitrogen. Now it is migrating from nitrogen to carbon. Now which is migrating origin? Migrating origin means starting point to migrate. Nitrogen. Where it is ending its migration? Carbon. Now this is terminus. It is origin. Who is migrating? Methyl is migrating. Methyl migrating in the form of electrophile or nucleophile? Electrophile. This is anion. It is attracting this cation. Is it anion or not? This anion attracting this cation. Now cation migrating from nitrogen to carbon. That's why it is called cationotropic rearrangement. Rearrangements are three types: cationotropic, anisotropic. What is one more? Free radical. So in pinnacle, what we are generated? Carbocation. What is migrating? Anion. That is anisotropic rearrangement. But right now what we are generated? Carbanion. And what is migrating? So based on migrating group, you can say it is a cationic or anionic. Not based on generation. What we generated? Carbanion. What we are migrating? So whichever group we are migrating, based on their charges, we are classifying migrating rearrangements. Okay. Now anion is generated, carbanion is generated, now cation is migrating. So it is called 1, 2. What? Is it cationotropic or anisotropic? So in order to migrate this cation, what is required? Anion. So anion is helping for migration, or anion is helping for rearrangement. So that's why it is called cationotropic rearrangement reaction. So it is an example of Stevens rearrangement. It is Stevens rearrangement. You remember this. Conversion of quaternary ammonium to tertiary amine is called Stevens rearrangement in presence of lithium OMC. Now what is intermediate in this one? Carbanion. What kind of rearrangement it is? Cationotropic. On which basis you are saying it is cationotropic? Why? Because cation is migrating. Pinnacle is an example of anisotropic. Anisotropic are very high as compared to cationotropic. 90% of rearrangements are belongs to anisotropic. Very few are. So this one, Stevens, Somlet-Hauser, Neber rearrangement, okay, and one more Witting rearrangement. This all are belongs to cationotropic rearrangement. So it will, one more time it will comes in rearrangements, but right now you focus generation of a carbanion. cover. Now that is Stevens rearrangement. One more is there. This is called Wittig rearrangement. Concept is remain same. This is CH2 phenyl lithium. Where you remove proton? From CH2 or not? So when CH2 loses proton, now CH becomes carbanion which is stabilized by lithium, and this is O and this is CH3. Now what happens? See, this negative charge attacks on this carbon and this will migrate here. So when carbanion takes that methyl takes on alpha carbon. Now this will carry O minus and this is lithium. If lithium take water molecule, proton. If anion take this proton, and finally see what we are preparing now. This is CH3 and this is OH. So this is ether to alcohol or not? We are converting ether to alcohol by using a base. This is called Wittig rearrangement, not Wittig reaction. Wittig reaction is different, rearrangement is different. Both are not same. Don't think that if you write Wittig reaction, that is wrong. Wittig reaction is carbonyl compound to olefin. But Wittig rearrangement is conversion of ether to alcohol in presence of a base. What we are generating here now? Carbanion. After generating carbanion, that will attacks on this one. Now how it is migrating? How this methyl migrating? In the form of cation. Right or not? It is anion means it is attacks only on cation. Now where this cation present initially? On oxygen. Now where that methyl migrates? Methyl migrates from oxygen to carbon. This is called migrating origin and this is called migration terminus. These terms I will explain in rearrangement. Okay, it is an example of cationitropic or anionitropic? Cationitropic. Wittig rearrangement is an example of cationitropic. Stevens rearrangement, Somlet-Hauser, Neber rearrangement, Favorsky, even Favorsky also one of the example for rearrangement reactions. Proceeds with a carbanion. So this is last example. CH2, C double bond, and this is CH2Cl. You listen. This is most important one. See, these two are alpha carbons. This carbon carry halogen, this carbon carry no halogen. Now what I am using is, I am using NaOET. Now that will generate say carbanion on halogen free carbon. This is halogen free carbon. Now this will attack here and chlorine is removed out. After attacking, what you will expect? This is CH attaches to CH2 and this is C double bond. A carbonyl compound, cyclopropanone. So after getting the cyclopropanone, same reagent one more time I am using as a nucleophile. This will attack here, migrate here. So after migration, what you will expect? CH2, CO minus and this is OET, this one. Now this will migrate towards which side? This will migrate towards benzyl side. Why? Because if you migrate here, you will get stable, here unstable. So finally, inner carbon carry negative, and what about this one? Is it CH2? CH2. Next is C double bond, what is this? OET. And finally this will take proton, and what is final answer? This is CH2, CH2, COOET. What is this? Favorsky rearrangement. So what is intermediate in Favorsky rearrangement? Carbanion. So this is most important one. Cyclopropanone is intermediate in this one. One more is carbanion. Whenever if you are learning Favorsky rearrangement, think about cyclopropanone. And one more is carbanion. So after formation of cyclopropanone, now this reagent attacks one more time. Initially it is a base. What is NaOET? Base. First time this reagent is used as a base. Second time it is used as a nucleophile, that will attack here. After attacking, this reaction completely depends on ring opening only. See, this is a ring opening or not. When negative charge coming back here, it may open towards right side or it may be open towards left side. So can I open towards left side? Right or not? Why you are opening towards left side? Why? Because after opening you will get a carbanion. This carbanion always closer to benzene. If I open towards right side, what kind of groups are stabilizing this carbanion? No group. So that's why which is better? Left side. And finally, see, you will get this one. So what is this reaction? This is called Favors-key rearrangement. So this will come separately in rearrangements. Right now you take down only one example so that you can understand how carbanions are helping in rearrangements as well as variable concepts. So that is end of carbanions. Second intermediate is over. Clear? So what we learn in carbanion? Carbanions are excellent sources to involve in variable reactions such as chemical reactions are very important. So what are they? Substitution reaction, elimination reaction, chain lengthening reaction, rearrangement reaction, at last starting very important one, condensation. So in your chapters individually starting from alcohols, aldehydes, ketones, esters like that, almost all everywhere only one common intermediate will follow, that is carbanion. So that is end of carbanion. In your next class we will discuss about free radical as an intermediate. Okay, we will stop here, take a break. So you have an exam.